He is on the editorial board of several international journals, including Structural Safety, Probabilistic Engineering Mechanics, and Structural Control and Health Monitoring. He has published extensively in international journals, and his papers are very well cited. He has very high H-index. Now I will request Professor Manohar to make the keynote presentation.
Thank you, Balaji. Please confirm that you are able to see the screen.
Okay. I will just. Yes, I'm able to see the screen.
Okay, thank you. So let me begin with my talk. The title of my talk is Laboratory Testing for Estimating Reliability of Vibrating Structures. So this is the work done by 4 of my former students. I'm presenting their work on their behalf. Okay. So the problem that I'm talking about in this presentation is, suppose we have an engineering structure, not necessarily a civil structure, it could be a secondary system also, industrial structure also. And the scenario I'm imagining is it needs to be qualified for some dynamic load, and that dynamic load is modeled as a random process. For example, it could be induced due to earthquake or due to Guyave unevenness or any other source. The problem on hand is, how can we estimate the probability that the response stays below a threshold over a given duration? This is the problem of time variant reliability. So for highly reliable structures, with which we often deal with, this probability of failure could be very small, of the order of say 10 to the power of -4 or much less. So if you want to follow a simply a relative frequency approach, you need a very large number of samples to estimate these small probabilities. And that also implies long testing times and many other associated problems. Now, the question that we are asking is, can we reduce these test times? Or can we obtain acceptable estimates of probability of failure by using smaller number of samples? So the idea here is, the f of t is the test signal. So what I will do is, I will add a control force to this test signal, and under the combined action of this control force and this excitation, I will try to estimate the probability of failure. And this control force is selected in such a way that the sampling variance associated with the estimate of probability of failure is reduced. So the role of this control force is in some sense to promote failures, so that with fewer samples, we'll be able to estimate the probability of failure. But this control force should keep the estimate of the probability of failure unbiased. So it cannot alter the physics of the problem. The probability of failure estimator should be unbiased. So how do we correct for it? Having added this control force, you need to correct also. So this is the philosophy that is used in computational modeling of reliability. And the question that we are asking is, can we mimic this type of strategies in experimental work also? So the idea is to select the control force such that the probability of failure can be estimated with dramatically lesser number of samples. So to motivate that, let's consider a simple problem of evaluating an integral. I is a to b f of x dx. So I can write this integral by multiplying and dividing by b minus a. I can interpret this integral as this whatever is this integral as an expectation over a uniform distribution. So the problem of finding the integral becomes a problem of finding an expected value of f of x with respect to a uniform distribution. Now, then I can formulate an estimator. I can draw samples of x from a uniform distribution and estimate the integral using this estimator. So suppose I am interested in evaluating 0 to 1 x squared dx. The answer is known to be 1 by 3. Suppose I have shown here results with a different number of samples. So this is a log scale on x-axis, and the sample size need to be multiplied by 100 also. So you can see that 1/3 is the answer. And as we increase the sample size, you get more and more accurate answer. The sampling fluctuations keep reducing. Now, on the other hand, if I look at fix the 500 samples, the sample size to be 500, and repeat the test with 500 different sets of random numbers, then you see that I get these kind of realizations where the expected value is around 1 by 3, which is as it should be, and we get a distribution of the this estimated integral, And we can show that this is normal distributed, and there are many nice results that as n tends to infinity, this integral goes to the true value with probability 1. And central limit theorem ensures that this estimator is sampling distribution is Gaussian, and this estimator is consistent with minimum variance of this. If this integral is multifold integral of a large dimension, the sampling variance is independent of the dimension of the integral. So this remains, the sampling variance remains independent of size of vector x. So far so good. Now let's revisit this problem. What I will do is I will write I as x squared divided by pi of x into pi of x, where pi of x is a valid probability density function defined over 0 to 1. Now I will now estimate I by drawing sample from pi of x. Okay, so this is the estimator. Now in the previous case, as we saw here, if I want better estimate of this integral, I should increase the sample size. Now what I want to propose is that I will keep the sample size fixed, but I will choose this pi of x so that I can get a good estimate for acceptable estimate for I. So because the sampling variance now depends on not only the sample size, but also on this sampling distribution. So the strategy that we follow will not increase the sample size, but now I will sample from a sampling density function so that this variance is minimized. So for example, if you take pi of x as 3x squared, right? So integral becomes x squared by 3x squared into pi of x, which is, if you sample from this, you get the answer to be 1 by 3 for any value of sample size, and hence also true for one sample. So there is something miracle here. With one sample, I am getting the right answer. So where is that? Therefore, this sampling density function is an ideal sampling density. So what is going on? So this was my original probability density function, but now I am sampling from this red curve, and it gives exact answer with only one sample. So where did the randomness go? The catch here is that the definition of this important sampling density function requires the knowledge of I being evaluated. For example, if you am taking pi of x as alpha x square, to show that it is a valid density function, I need this value of this integral, which is what I am trying to evaluate. So in that sense, it is an ideal importance sampling density function, which I cannot know without knowing the answer. But the importance of this result is that such ideal importance sampling PDF exists, and we can develop suboptimal sampling PDF. So this is a well-known result. So I'm just giving this just to motivate you to understand what is the question. Now, this idea of importance sampling can be extended to a dynamical system. So you can consider now a state space model expressed in terms of a stochastic differential equation. This can be any size now. Suppose we are interested in finding the probability, call it a probability of failure, that some function of the response vector stays below h star over a time duration 0 to capital T. I mean, this limit state is violated. Okay, so this is the highest response over this, and h star is a permissible value. So again, if I do a brute force simulation with N1 sample, I get an unbiased estimator with this sampling variance. Now, to reduce the sampling variance, I have to increase the sample size, this N1, which I don't want to do. So what I will do now is, I will add a control, artificial control to the excitation. This is my excitation. I will add this control. And to keep the estimator for the probability of failure unbiased, I need to evaluate what is known as a Radon-Nikodym derivative. It can be shown, I'm not going to get into that. You are interested in this expected value of this indicator function. It can be evaluated now in terms of this x tilde and gamma using this formula. Okay, now this here in this, now there is sample size N2. Now this control force is now available. Just like pi was available to me, this control force is available to me. So can I select now the control force that is sample size N2, and this control controls the, contribute the variance of the estimator. Now the idea is to use this control force to bring down the sampling variance. So in fact, you can show that there is an ideal control where you get the exact answer with one solution, just like I did for that integral. Okay, it is also possible, but the formulary is a bit more complicated. So again, the question is, to find that magic control, you need to know the answer. So therefore, the issue is not about finding that ideal control, but can we find suboptimal control, right? So this theory is developed in the existing literature. And one of the strategies that is proposed is to use a distance minimizing suboptimal control. That means this control is selected so that we consider this equation. For example, if it is linear problem, we can write in this manner, and we can select this control so that the measure of this distance is minimized. It's like a, reliability index and things like that. I mean, I don't want to get into that, description, but anyway, there is a theory for finding this control. And this control involves the impulse response function of the system that we are studying. This is what is the model available in computation. Now the question is, if I think of doing developing an experimental protocol, we need to find this control and the Radon-Nikodym derivative. So it turns out that we observed that we don't need a mathematical model to establish the suboptimal control and the Radon-Nikodym derivative. Whatever is the information needed to construct this control and the correction, we can experimentally determine, no matter how complicated the system is. That means I need not have the mathematical model for the system. I will conduct a series of tests, simple tests, which helps me to define that control and the correction term. So if that is the basis of what we are talking about. So to implement that, we considered a family of systems. We began by considering a fairly, conceptually difficult frame, a system, which is a 5-story frame, which is bending torsion coupled. It has one of the column is aluminum and other 3 are steel, and the masses are eccentrically placed on the slab. And you see here diagonally there are blue lines. They are all wires, and this we tested on a multi-axis shake table that we have. We subjected it to biaxial support motion like this. And the question is, can we estimate the reliability of such a system by using few samples? Okay, maybe it is strain in the column exceeds some value or something like that. So after having got confidence in this, we extended it to a fairly more complicated system, testing an automotive system on a 4-post rig. I will come to that. So coming to this first problem, we modeled the ground motion as a non-stationary random process following this well-known Kanai-Tejumi arguments, and this can be written in the state space form. I'm going. This is an envelope function, and we can simulate, and the samples look like this. And I'm going to skip this. So there is a part of the experimental work which determines the control force, and part of it determines the correction. And once they are determined, a series of tests are done to estimate the probability of failure. So these are some of the details of how the control is obtained. I mean, I'll just flash them. I'm not going to get into it. It involves a lot of descriptions. Get into the details. So here, the blue line is the original time record, which we should have applied on our shake table. But this red one is the one where the control force has been added, that intelligent control, right, which promotes failure and helps us to estimate probability of failure with smaller samples. So once that is done, there are some more samples. This is a correction that we need to do. This is called Radon-Nikodym derivative. This is also experimentally determined. And here are some plots of probability of failure using this method. So just to make sure that we are on the right track, we kept the failure criteria so that we can verify by direct testing. So we tested about 1800 time histories were applied. And with 250 samples using the modified theory, we got similar results even for low probability. So this is, we considered a nonlinear frame under biaxial ground motion, and a probability of failure of as small as 10 to the power of -6 was obtained using 250 samples. And it cannot be validated. It's very difficult to validate. Y-axis is on log scale. So this blue line is some kind of validation exercise for high probabilities of failure. So you can see that I don't have support for experimental support for accepting or rejecting these 2 points, but the trend indicates that, there is every reason to believe that we are on the right track. Okay, so this is what is the main, outcome of this type of study. That means I can find probability of failure as low as 10 to the power of -6 for such a complicated system, a system undergoing biaxial support motions, having bending torsion coupling, geometric nonlinearity, etc., with 250 samples. Next, one of the questions that we considered further was that there will be many engineering systems where there are active control elements. And the role of those active control elements is to prevent failures or mitigate the response. So when I add this control force to, if I am testing them for reliability, then when I add a control force, how will these control elements behave? There is the control force that I add is supposed to promote failure, whereas the control that is physically present need to bring down the response. So a question arises whether there will be a conflict. Mathematically, you can show that there won't be any such conflict, but to make sure that our understanding is right, we tested one 3-story multi-story frame with a MR damper, which is an active element. And again, I'll not get into the details. We showed that we could get good estimates for probability of failure as low as 10 to the power of -6 with about 250 samples. Then we considered more complicated system, that is road loads on a vehicle like this, and the road loads were modeled following a suggestion made in existing literature as a filtered white noise process. And the rear wheel sees this load after time gap because we assume that they are moving on the same track, and this model allows for dependence between the two tracks, and various complications can be allowed. And this test was performed by one of my students who was an engineer at BIS, at the BIS premises. And again, here we were able to show here the question. We can ask many questions on ride comfort and many other issues. So he focused on acceleration levels at certain points, and he computed the reliability. And we also considered failure modes in series and failure modes in parallel, and showed that with reasonably small samples, even system level reliability could also be estimated under time variant system reliability. So at this stage, one of the weakness of this approach is that for every level of threshold value, we need to find different controls. But the control that I find for this level doesn't work for the next level. So this may be a problem if one is interested in getting a complete picture of such graphs. So another way to do that would be to follow a different philosophy, that is the so-called subset simulation philosophy, which emerged in early 2000. And that we have modified to mitigate some of the inherent weaknesses in that. And we have combined Markov chain splitting with subset simulations. And this paper has appeared in Probabilistic Engine Mechanics. And we created an experimental protocol which mimics this, where again, let me emphasize, I don't need the mathematical model for the structure being tested. I don't need its finite element model. Whatever information I need, I generate purely experimentally. So here, again, we considered, I think here we considered uniaxial support motion, and we assumed that support motion is a filtered white noise, and we were able to, discretize that in terms of Gaussian random variables. So the question was, if we select a performance function and define a limit state in this manner, what is the probability of violation of this limit state? And we're assuming excitation could be non-stationary or Gaussian or non-Gaussian. Support motion could be biaxial, multidirectional, etc. There is no restrictions on that. So the story is, we start by simulating few trajectories of support motions, and then define an intermediate failure level and identify those trajectories which lie, in the failure region of this intermediate failure region that gets automatically defined. And from these points, we run Markov chain Monte Carlo and generate additional excitations, which are then again applied on my test system, and that defines further next level of failure level. And this continues till I reach my target failure probability. So at every time, I need to have the control software of the shake table has to be integrated with a MATLAB or other source where I am running this subset simulation code. So that my students did that. So the details are here. If you have any questions, I will direct them to my students. So this one of the problems in implementing MCMC is there is what is known as a burn-in time. So burn-in time is needed to ensure that we have to dissipate some transients that are there in the simulation to reach the target PDFs. So during the burning time, we don't want to do the test. So to ensure that, what we did was we incorporated a surrogate modeling at every step, where for purpose of removing the burn-in, we didn't conduct actual experiments. We ran it on a surrogate model, which was built using experimental data. Again, there is no need for FE models. So that's worked, and we were able to test couple of experiments. We did experiment on a reaction wall on a 2-story frame. Again, here we added diagonal wires to the system to create nonlinear effects. And Sonal, who worked on this, did extensive studies, and some of these results are shown. Again, the story is that with reasonably small sample size, we are able to estimate small probabilities of failure. And the merit of this method vis-a-vis the Girsanov transformation method that I mentioned earlier is that I get the entire curve here in one stroke as the subset simulation proceeds. So we repeated this on shake table on a L-shaped frame with biaxial bending and all that. Again, a system reliability study was also done, and we got, again, very small probabilities we were able to estimate using small samples. So in closure, I would say that the important sampling strategies which have met with success in computational modeling, we can embed them into experimental protocols to estimate time variant reliability. So what we have done is we have considered geometrically nonlinear building frames, biaxial earthquake support motions, and 4-post rig with biaxial, 2-lane guideway unevenness, and even as structure with active control devices. And we have tried out 2 such sampling variance reduction strategies, namely Girsanov transformation, that is a control force based method, and the Markov chain splitting methods. So, so far we have investigated limit states pertaining to violation of serviceability conditions. So the main feature of this is that we are able to experimentally interface intelligent sampling procedures with control algorithms of the test equipment, because whatever excitations we produce has to drive our control software of our actuating system. So that interfacing has been done. And actually, we need not model the structure. So you can test very complex systems, battery racks or things, computer hard disk or things like that, which are difficult to model. So, and we can automate the entire process. We tried, doing that with a minimum human intervention. Now, the assumptions that we have made so far in our work is that only the excitations are random, and also the structural behavior is within elastic limits. And also another important assumption is that whatever quantities are needed to define the limit state, as far as the system response is concerned, we should have an ability to measure them, the strain at a point, or displacement at a point, or acceleration at a point. You should be able to measure. That much measurement has to be done. No other measurements are needed. Now, the question is, all the assumptions that we have made, can we relax? I mean, it's a nice way to, just ponder over that. So if you want to test, for example, systems with parameter uncertainties, then you need to produce an ensemble of structures. Okay. So the question is, can we again use importance sampling for that? So instead of testing 500 samples, can we test only 25 or 30, where those 25 and 30 are produced through an intelligent importance sampling strategy? So, for example, I could think of is you can combine 3D printing with an ensemble to produce an ensemble of intelligently designed inhomogeneities. So you can handle geometry, but material inhomogeneities, I don't know how to do it. Maybe 3D printing might be able to do it, but I don't know about that. And also another possibility is we can investigate systems with localized nonlinearities. For example, you have shock absorbers or vibration isolators where nonlinearity is confined to only that. Then, the main body of the system can be, still linear, but nonlinearity can be localized, and that part can be replaced, and we can test an ensemble. So these are some thoughts, and I just thought I will share our work in this. So these whatever ideas I presented have appeared in recent years in these journals. If any of you feel interested, I can share the papers with you. So let me close by thanking the organizers for the opportunity provided to share our work, and also audience for the attendance and attention. Thank you.
Thank you, Professor Manohar. If anybody is having any question, they can ask now. Professor Manohar is there. I request.
If can I ask one question, Mr. Manohar?
Yes, please.
Mr. Manohar, it is a mix of question or the future activities that we are going into the probabilistic seismic evaluation, or rather I would say probabilistic seismic probabilistic safety assessment, where we have to create the floor spectra and then eventually evaluation of the failure probability and then fragility and then failure probability. There are some components where answers are not ready-made available and they require some experimental, experiments to be carried out or design of experiment even, So, how far the methodology that you discussed, it can be, or as a complete package. Suppose if I have first floor, second floor, third floor, I have excitation, spectra and all that. How you can help us to complement the seismic probabilistic risk assessment activities, because we have a PRA model of the plant, and then now you have to see how if we have a certain level of seismic event, where certain events are requiring a real experiments actually, on the vibration table. So could you help us? And if you could help us, what should be the framework?
See, the experimental protocol that I have been discussing is basically meant to address the type of question that you are, raising. So presently, I can say that it's feasible to do that. So what needs to actually go ahead with this is the shake table on which you are going to test the system will be typically a controls, feedback control system. So it will have certain controllers. So we have to develop a code to interface the sampling of excitations, which drives those, the controls for which basically it provides the inputs for your shake table, and that tracks the active, the control device of your actuating system will track that ground motions. So if that protocol is set up, any qualification test which you carry out in a deterministic manner, that is for one excitation which is compatible with some spectrum, etc., can now be carried out for an ensemble and with minimum time. I mean, even if probability, suppose you claim that the probability of failure for a certain level of excitation is 10 to the power of -5, how do you validate that? By doing 1 or 2 tests, you can't validate that number. You can only do for some scenarios. So the point that we are making is you can test for reliability. That is a small number. So this is an idea. If you are doing computational modeling, the literature on computational prediction of reliability is so extensive that this is a very common question. How do you find small probabilities? So much development is taking place on importance sampling, machine learning tools based techniques, response surface based techniques. So many things are happening, but there is no such similar development when it comes to experimental validation. That is that the computational models will not be able to work very well because you will have a lot of difficulty in making a valid FE model for the test structure. That is why you first of all, you go for an experiment. If there is fluid structure interaction or some other complication, right, some temperature related issues, etc., it can be done. This is my feeling. I mean, this is at a research level, and it has gone through reviewing in, a few good journals. I expect that it has merit to explore. Yeah. So I would be very optimistic in, taking up the type of question you were mentioning.
Maybe I might come to Bangalore to discuss this problem and, modalities, how it can be. If you can.
You're most welcome. Yeah, you're most welcome. The idea of this type of meetings is to, trigger that type of discussions.
Thank you so much.
Thank you, sir. Any other questions? Any other questions? Anybody would like to ask? Hello? Participants? Anybody would like to ask any question? Professor Manohar? Okay. Professor Manohar, I have a small doubt. It is not a question, please. It is a doubt I have. As you rightly pointed out, the limit state that you are considering corresponds to the serviceability limit and the assumption that the structure is going to be elastic. Now, that is consistent. Serviceability limit state and elastic behavior, they are very consistent. But if we look at the, I am talking about generally these civil engineering structures. I'm not talking about the special structures, critical structures such as nuclear power plants, and also the hospital structures, like for example, the operation table and all that, or any other, MRI scan equipment. Generally, what they try to do is, if serviceability limit states are considered, the failure probability allowed is of the order of 10 to the power minus 2, 10 to the power minus 1. So that's quite a high failure probability. And your method it has been validated around those values. I mean, it works exceedingly well. So it gives a clue. Even for the other structures too, this method can be applied with limited number of experiments. We can validate the satisfaction of satisfying the limit state, serviceability state. That way, I wanted to say that it is an excellent, what I should say, the kind of ideas that you have presented, the kind of experimental details that you have presented, how you have overcome the difficulties. So I think that's an excellent presentation, and it is equally applicable for the other field also. That's what I wanted to say. Yeah. So thank you very much, Professor Manohar. If no other questions are there, it was a great learning for me. So thank you very much, and it was very nice and excellent presentation. Thank you very much.
Thank you so much. I appreciate it. Yeah. Thank you.
Madam, it is over to you, madam.
Thank you. Yes. Thank you, Manohar sir and Balaji Rao sir. So next technical program will begin with the paper presentations. That is technical session 8. Please move on to the breakout room. And the remaining, that is technical session 7 authors, please stay here. In technical session 8, we have A10, A27, A39, A12, and A30. And in the main room, we will have the authors for A46, A48, A56, A55, and A14.
I find all the authors of technical session 7 present here except A56. With the author M.E. Ramarao and Andrew Paunaka, if anyone is present, please indicate. And also for technical session 8, I could not find the author of A39, that is R. Kavita, Optimal and Intelligent Model of Data Protection Techniques in Cloud Storage, a review. So except these two, I think 4 papers in each, 4 authors in each session are present now. Then Dr. Sujata, you please take over the session TS 8 in the other room. I'll coordinate the technical session 7 in the main room, if it is okay. Hello. I think Dr. Sujata has gone to the breakout room already.
Yes, I think so. Yeah.
Okay. We will start the technical session 7 here. On behalf of the organizing committee, I have the pleasure in introducing Professor Sayan Gupta, who will be the chairperson of the technical session 7 on structural reliability and health monitoring, part 2. So I have a brief introduction about Professor Sayan Gupta. Professor Sayan Gupta is a professor in the Department of Applied Mechanics, IIT Madras, where he currently leads the Uncertainty Lab. His core areas of expertise are in nonlinear dynamics and uncertainty quantification. His current research focus is interdisciplinary that include climate dynamics, brain dynamics, non-smooth dynamical systems, dynamics of complex networks, fluid structure interactions, and energy harvesting. He has also extensively worked on structural reliability, random fatigue, system identification, structural health monitoring, uncertainty characterization in materials, and lifetime predictions. Professor Sayan is currently spearheading the Center for Complex Systems and Dynamics at IIT Madras, focused on interdisciplinary research and comprising of faculty from departments of engineering and science. He has also been instrumental in starting the new interdisciplinary dual degree program in complex systems and dynamics at IIT Madras. Professor Sayan holds a bachelor's degree in civil engineering from Jadavpur University and did his master's and PhD from Indian Institute of Science, Bangalore. He has held short-term positions in universities in Netherlands, Canada, and Sweden. I now invite Professor Sayan Gupta to take over the session.
Thank
Seven.
you, Dr. Senthil
Yeah.
Kumar.
Yeah.
Am I audible?
Yeah, you are, sir.
Yeah. Okay. So in this session, welcome everyone to this session on structural reliability and health monitoring 2. And I understand there are 5 presentations in this session and 4 of the authors are present. Only A56 is not yet available. Am I right?
Yes, sir. You're right.
Yeah. Okay, so we will go with with whatever is available, whoever is available. So the first paper is authored by Abira Radar and C.S. Manohar, and the title is Probabilistic Model Reduction in the Analysis of Randomly Parametered Building Frames Subjected to Sudden Loss of Columns. So yeah, if it is going to be presented by Abira, right?
Yes, I'll share my screen. I am audible, right?
Yes, you are audible. And
sorry to intervene. There is one announcement. The chairman of the session can finally, after the conclusion of this session, can give a half a page or 1 page summary report of the session and also the ranking of the papers.
Okay. Yeah.
Thank you.
Thank you. Yeah. Yes, Abida, you can go ahead and share the.
Okay. It's taking me some time to share the screen. I'll take a moment.
No problem. I will take. Don't get nervous. You will see a share button.
Yeah, it's actually asking me for permission, so that's why it's taking some time.
Did we lose her?
Probably we can start with the next paper and come back to this later on.
Okay. The next paper is paper number A48. Is the role of interfacial transition zone on response of concrete under tension, a micromechanical approach. Authors are Nikhil Gupta and J.M. Chandrakishan.
Yes, I'm here. Can you hear me?
Yes, Nikhil, I can hear you. Please
I'm
go
sharing my screen.
Actually, can I try to share my screen again?
Yes.
Okay, let us try, Abira.
Should I stop?
Yes, Nikhil, can we just stop?
I'll wait again.
Is my screen visible? Hello?
No. Yes, Abira, your screen is visible. Yeah.
Okay. Good evening, everybody. I am Avira, and today I'll be talking about probabilistic model reduction under sudden column loss. This is the outline of my presentation, and I'll start with background to the problem. The presentation is in context to disproportionate collapse of structures. Disproportionate collapse of structures, it takes place when an unforeseen event leads to a local damage and and due to the inability of the structure to contain this local damage, it spreads and leads to the collapse. Some of the examples of these types of collapse are the collapse of Ronan Point, which took place in 1968, in which a gas cylinder explosion at 18th floor led to the loss of a wall and then ultimately the collapse of whole bay. One more example of such a collapse is that of the collapse of Alfred P. Murrah building, in which a bomb blast outside the building destroyed one column, and the damage then spread to 1/3 of the building. So what happens during this abnormal load and how it is different from other types of loads like earthquake loads and wind loads is that first, loads like earthquake loads and wind loads, they act globally on the entirety of the structure, but this abnormal load, which can be anything and it's not defined, it's like very highly localized. Another is that depending upon the geographical location, we know that a structure might like envisage earthquake loads or wind loads. Hence, they are anticipated loads and they can be taken into account at the design stage of the building. But these abnormal loads, they are unanticipated loads, and normally they are not taken into consideration at the design stage. Speaking in probabilistic terms, if we want to define probability of collapse of a structure given an abnormal event, it can be defined as the product of three probabilities, as is shown over here. So, in case of these unforeseen events, the probability of occurrence is difficult to define, and hence this probability of P of E cannot be defined, and hence we cannot define the term probability of local damage given the abnormal event. So this problem is dealt by taking the product of these two probabilities and equal to 1, and hence the probability of collapse is just the collapse of the structure given the local damage. So also one more term relevant to disproportionate collapse is robustness, which indicates the resistance of the structure against disproportionate collapse. So so if we cannot really define the load or the abnormal event, so the question is like, how do we take into consideration such an unforeseen event and such an abnormal load at the design stage, or to check if my structure is safe against it. So what is done is that, as is mentioned in the title of the presentation, sudden column loss. So if we have a pristine structure and we assume that due to an abnormal load A, a load-bearing member, like a column is suddenly lost. So when this column is suddenly lost, there are two things that happen. One is the previous load paths that were in the structure, they change, and two, there is a sudden redistribution of loads that were previously carried by that member, and since these loads, they are like, there's a sudden redistribution, it leads to the transient dynamics in the building. So sudden column loss is a way in which the unforeseen event and its consequence is taken into account at the design stage, or to check the stability of a structure against unforeseen event. So what we expect under a sudden column removal scenario is that my structure should be able to develop alternate load paths, and it should be able to carry the additional loads, and this kind of forms the whole philosophy of design against disproportionate collapse, and it's also known as alternate load path method, as is mentioned in the codal provisions like UFC and DOD. This alternate load path method is also known as threat independent approach, because we are not really modeling the threat, but we are just dealing with the consequence of that threat and how it affects the response of the structure. So in the in this study, the objective is that the objective is to identify the most influential random variables that affect the peak vertical displacement at this location at the node of column removal. So the tools that have been used for that is the global response sensitivity analysis. So the objective is to perform global response sensitivity analysis and to rank order the most influence and to rank order the input random variables and to ultimately obtain model reduction. So starting with what is global response sensitivity analysis, if we consider any function y is equal to f of x, so where xi represents the input random variables and y is the output, and this function can be anything, an equation, and in the present case, it's a nonlinear finite element model. So the method, the global response sensitivity analysis method that has been employed currently is the factor mapping method. In this factor mapping method, after we have performed the nonlinear analysis, we have an output. This output random variable space, it is divided into two regions, a behavioral region and a non-behavioral region. Then these behavioral and non-behavioral regions are mapped back into the input random variable space, which leads to the development of two sets, behavioral sets and non-behavioral sets of the input random variable space. And the concept is that the distance between these two sets for each of the random variables is determined. So if this distance tends to 0, or the normalized value of this distance tends to 0, the random variable will have no influence on the output. But if it tends to 1, it will have a large influence. So in this present study, 3 measures of distance between the two between the behavioral and non-behavioral set have been used. Now, the most commonly method used is the KS statistic, but in this study, two more distance measures have been used: the engineer's metric and the Kantorovich metric, which have been defined in this table. So the frame that is considered for the study is this steel moment resisting frame, 4-bay 3-story frame, and a total of 132 random variables have been considered, which is shown in this table. So the details of the random variables and their probability distribution is shown here, and correlation coefficients for the material parameters is given. So the problem of disproportionate collapse is a highly nonlinear transient dynamic problem, and the type of analysis that is performed is nonlinear transient dynamic analysis. OpenSeas is an open source software that has been used for FE modeling to model the material nonlinearity. Distributed plasticity elements have been used, and to model geometric nonlinearity, co-rotational transformation have been used. MATLAB has been used to simulate the random variables, and total sample size of 10,000 has been used, and MATLAB and OpenSeas together have been used to run the simulations. So column C2 has been suddenly removed, and we are monitoring the displacement at node 22. So these are the results of the sudden column removal. Figure 1 represents the ensemble of response, and figure 2 shows the inelastic action that occurs during the oscillations following sudden column removal. So based on this ensemble of response, 2 behavioral sets have been considered. First, the response quantity that of interest is taken as the peak vertical displacement after the column is removed, and 2 behavioral sets B1 and B2 are taken for sensitivity analysis. So these are the results of the factor mapping, and the results have been plotted in figure 3 and figure 4. So figure 3 shows the normalized distance measures for three statistical distances, and we can see over here in the figure 3 they have been arranged in terms of the different groups, and we can see that here the dead loads play a major role. In figure 4, the same distance measures have been plotted in an descending order, and we can see that almost like more than 80% of the response is just 20 random variables are responsible for more than 80% of the response. And also we can see all the 3 distance measures, they give a similar trend, like at least up to 0.2, around 20 random variables. So the results of the rank ordering, they are not clear from this figure which random variable is contributing. So the first 15 random variables have been put like shown in this figure, like which random variables are most influential. And here we can see that loads in elastic material properties and some of the elastic constants are important. And all of these random variables, they are actually they correspond to the beams of the in the bay of column removal. So this figure 7 and figure 8, they show the results of model reduction for two regions that were selected, B1 and B2. It can be seen, it was found that 30 random variables were enough for model reduction in the region of interest B2. It was seen that the
Abhira, can you please try to finish in another 2 minutes?
Yes. Yeah, this is my last slide. So in the region of interest B2, 30 random variables were enough. And it was seen that the results of Kantorovich metric were the most, it gave the most correct results, and like the minimum number of random variables that were available for model reduction. And if we considered, like for the like region of interest B1, if we consider just the 30 random variables, first 30 random variables, the results were not that satisfactory, which showed a dependence of the region of interest on the model reduction. So that was my presentation. So a scenario-based threat-independent approach was used to study the response of structure against unforeseen events. So the parameters that affect the response, the maximum vertical displacement after column is removed, they were determined using global response sensitivity analysis. So we began with a model of 132 random variables, and it was found that 30 random variables were enough to understand the response of the structure, that they were the most influential. Dependence on the choice of behavioral set and also on the measure of statistical distance was observed, and this is something that can be explored further. Also, the use of statistical distance to quantify robustness is being explored further. Thanks.
Thank you, Abhira. That was a very nice presentation. Okay, the floor is open for discussion for any questions. Anyone has any questions? Can you please then raise your hand? Okay, I have, yeah, anyone has any
No,
questions?
please proceed. I will ask after you.
Okay, Abhira, I just have one question.
Okay.
You started talking about random variables.
Yes.
So what was the principle behind considering random variables? Why are you considering them as these certain properties as random variables?
Normally, like we cannot consider a system as deterministic because there are so many, like there will be so many variables.
I mean, so basically these random variables would be anywhere there irrespective of whether there is this type of sudden collapse or not. That's what you're trying to say. It's not that because of the sudden collapse that these random variables are entering into the problem.
No.
Okay. So that brings to the second question. Because of this sudden collapse, do you think that there should be some additional uncertainties that will enter into your model, which otherwise would not have been there?
Okay. I don't think I can answer that question right now, because the uncertainties, like if I were doing an earthquake like analysis on the structure, I would consider the same random variables that I'm considering right now. Like I have not considered any like special random variables just because I'm doing a sudden column removal scenario. So maybe I can look into it, but right now I have not
okay,
thought about it. Like if any other different random variables will be more relevant as compared to a normal structure or not.
Okay, thanks.
Shayan, can I say something just briefly?
Yeah, please go ahead.
No, I think the randomness could be on the location of the where the abnormal event takes place. which column to be removed, how many number of columns can be removed, and the level of damage in a column, it can be partial. Basically issues like that can be included, but the whole idea is we don't want to model the initiating event. So many things go out of the equation. Because if you start doing that, then you enter into a new, complex physics, which we don't want to model.
So that's why you had considered the two if probability conditional probabilities right at the beginning. You have removed them.
It is a scenario-based study where we look at only consequence.
Okay. Yeah, I think Professor Dr. Balaji Rao had a question, right?
Yes. It is quite possible that I missed the point, but I would like to ask a doubt. Maybe you have presented, I have not seen. See, in this kind of nonlinear transient dynamic analysis, damping plays an important role.
Yes.
Now, has the damping been considered as a random variable? And it is variant with respect to the location of the damage, you see?
Okay, so I'm not considering damping directly as a random variable, but the way my software works is that it's deducing the, I'm using Rayleigh damping, 5% stiffness proportional damping, and it's calculating that damping based on the material properties, like all the properties of the frame itself. So in some way, yes, the randomness in the damping is being considered, but I'm not directly providing a random model for damping. I'm not providing a probabilistic model for damping, but due to the randomness in the properties, material properties, and randomness in the loads, it is implicitly being taken into consideration. But I'm not modeling damping as.
The reason why there is an important role. The uncertainty associated with damping is very high.
Okay.
And when we are trying to do the nonlinear dynamic analysis, I think damping plays a great role.
Yes.
Shayan, can I just add one line?
Yes.
See, the issue is we are considering inelastic energy dissipation automatically because the material constitutivity allows for elastic, yielding and other things. So hysteretic energy dissipated is automatically taken care of, and that is random. But this initial linear damping, may not be very crucial because this is a large deformation and material nonlinear behavior problem. So in some sense, energy dissipation has been modeled as random. Initial damping, yes, if your response is limited to linear behavior, what you say is true, but we are far exceeding that.
Okay. But depending upon the location of the damage, will the hysteretic behavior also change depending on whether it is a shear pitching or whether it is going to be a fractional failure? The hysteretic behavior itself may change, right? I don't know, maybe.
Okay, I think we'll have to move on to the next speaker.
Okay.
Abida, maybe you can take this up offline with Dr. Rao. Okay.
Okay.
Yeah. And that was a very nice presentation. Thank you very much.
Thank you.
And we'll move on to the next speaker. Next speaker is Nikhil, and he'll be talking about role of interfacial transition zone on response of concrete under tension, a micromechanical approach. And the paper is co-authored by Nikhil and J.M. Chandrakishan. Yes, Nikhil, please go ahead.
Can you, is my voice and slides visible?
Everything is visible, yeah.
Okay. So good evening all. I'm here to present my research work titled as Role of Interfacial Transition Zone on the Response of Concrete Under Tension Using Micromechanics. So to talk about the background, the concrete specimen is subjected to uniaxial tensile loading is considered. The figure 1 shows the represented volume of concrete with a microscopic view in the right, showing all the 3 phases of concrete. Now the question arises how to model the interface layer. The literature suggests 2 ways in which it can be modeled, in which interface can be modeled. The first one in which interface has no thickness and cracking is governed by the displacement discontinuities occurring at the interface. The second one is where interface layer is modeled as the third layer with different material properties. The stresses and displacement are continuous in this case, and cracking is generated within the XZ layer. The work on the second approach is not done yet, thus I have worked on the second approach, which is also depicted in this figure 1. So The first work is to compute the stresses in the ITZ layer. The model from the literature is considered to achieve the objective. The equations are plotted in the, with the material properties in the MATLAB, and variation of volume fraction is also included. The left curve shows the variation of stress in the radial direction with theta from the zenith point. Theta can be referenced on the this figure. So the right curve is for the principal values of the stresses with respect to theta. Both curves are varied with the volume fraction of aggregate as 0.35, 0.45, and 0.7. So the result suggests that for the constant volume fraction of 0.45, which is this red curve, stresses in the ITZ zone is increased by 21%, and the cracking starts at theta is equal to 0. Also, this at this volume fraction of aggregate, amplification factor of principal stress, which is in the second curve, is raised up to 22% with theta pi by 8 for the tensile loading and pi by 6 for the compressive loading. With increase in the volume fraction of aggregate, the amplification factor decreases. This is because the macro stress is distributed on more aggregates, thus reducing the concentration of each aggregate interface stresses. So the next mechanical model is proposed in this paper, in which macro stresses are applied, is distributed in all the three phases according to the volume fraction of each phases, which is represented in this equation 2. Where capital sigma is the macro stress applied at the macro level, and other sigmas are the average stresses for each phases, and F are the volume fraction of each phase. It is being assumed that all voids are filled with mortar. Thus, sum of 3 volume fraction is equal to 1. And from equation 2, average stress in the mortar can be computed as shown in this equation number 3. So average stresses, as we know, in other phases can be computed by the averaging the integration over the volume of that phase like this. But in our model, the equations discussed in the previous sections will be utilized to compute the stresses. Next, these stresses are upscaled, and macroscopic constitutive relation is presented in equation 5. As RV is assumed as isotropic, the complex matrix is represented, is assumed, is presented here. For each phase, elastic modulus and Poisson's ratio are changed accordingly. So the next thing to discuss is what happens when micro cracks are initiated. First thing is the introduction of elastic modulus and Poisson's ratio, which is given by the formula as shown. Here the crack parameter is defined as the product of number of crack per unit volume and the cube of mean crack radius, which is generated when the cracks are initiating. So the second is the introduction of volume of cavity, which is initially assumed as 0 due to the micro cracks. Thus, an extra term is introduced in form of a volume of cavity. The value of volume of fraction of cavity is calibrated with the experimental data, and it is assumed that same increment will be observed for all load step. The effect of including this is on the volume fraction of other phases, which are reduced by the factor of 1 by FC at each load step. So now to define the failure criteria, the material fails when one of the mortar or the RTZ layer reaches its final strength. The numerical algorithm will be presented in the flowchart, which is adopted here. The volume fraction of cavity is assumed. Let it be start with 2% of the volume fraction of ITZ present. In step 2 and 3, the values of volume fraction of ITZ, parameters, and B volume and B parametric is calculated. These are the parameters which are used for calculating the ITZ stresses, stresses in the ITZ layers. So in the next step, the macroscopic stresses and the mortar stresses are initialized as 0 to calculate the stresses in the ITZ layer. This stresses in the ITZ and mortar layer are compared with the initial values of the initial strength values of the initial strength value of the corresponding phases. The initial values correspond to the stresses at which the micro cracking starts, as we discussed in the previous slide. If value of stresses are lower than the initial strength, the macros will start strains are computed from the constitutive relationship. The stresses are macro stress are increased by 0.1 megapascal. If not, the next condition will be compared with the stresses in the ITZ layer, which is greater than the initial strength and less than the final strength. But mortar strength is lower. Is lower. So is lower than the corresponding strength. So for validity of this condition, elastic modulus of the ITZ layer and volume fraction of each phase is changed accordingly. And the updated value of EITZ are supplied to the the constitutive relationship to get the further stresses in the response. Further, when micro stresses are increased and mortar stress may cross the initial strength, for that case, elastic modulus of mortar is also reduced for before calculating the microscopic strain. Iteration is stopped when either of the two mortar or the ITZ stress reaches the final strength. This response is matched with the experimental data, and value is increased until the experimental data is matched. So these are the equations for the reference and the data which is being utilized for this analysis. So talking about the results obtained, the first result is the response obtained by the model proposed. The model shows perfect result for the calibrated values of volume fraction of cavity as 0.00013, which is approximately 5.7% of the volume fraction of the ITZ layer presented in the around the aggregate. The micro cracking starts at 2.1 megapascal, which is 58% of the peak load. So the next curve is the average stress in the each phase. The stress in the each phase at the failure point can be computed. It shows that the maximum stress at the failure point occurs at the in the ITZ zone. Hence, the failure starts in this zone. Next result shows the decrement of the elastic modulus of the concrete, which is presented with respect to first in this figure 7 as respect to macro stress, and with respect to crack parameters in figure 8. The total decrement of 21.64% is observed in both cases, and it can be viewed only when the micro cracking starts after 2 megapascal stress is reached. So moreover, the figure 8 also suggests the decrement rate is slower when the small stresses are there and faster for the high stresses. This is due to the higher number of and size of the cracks which are occurring at the highest stresses. The result suggests the crack parameters, which is calculated and observed at 0.0138. Which is utilized for commenting the number and size of the micro cracks generating further. Thus, a 3D plot is generated with the variation of crack parameters on number of cracks and mean radius. It can be observed that for initial number of cracks as 2000, which is this with a mean radius of 0.0019, and at a failure number of failure. The number is reduced to 500, which mean radius of 0.22. This decrease in number of is correspond to the merger of smaller cracks into larger ones, as the radius is increased and the number is decreased. So the next two graph shows the variation of crack parameter, keeping the third variable constant. For figure 10, for constant n value as 2000, the mean crack size increases. Crack size increases from 0.019 to 0.03. The values can be computed for other constant values of n also. Thus, in this case, no new cracks are generated, but the initial cracks are increased in size till failure. In figure 11, for constant mean radius of crack as 0.02, the number of cracks increases from 1725 to 27600 per unit volume. This can be calculated for different values of constant mean radius also. Thus, in this case, new cracks are formed at each load step with constant mean radius till failure. These are the two observations with some assumptions. So if we carry forward about the research with the parametric analysis, next results deal with the parametric analysis in which first parameter is volume fraction of aggregate, which is varied as 0.35, 0.45, and 0.7, keeping the diameter constant. Since the aggregate has the highest strength in all three cases, the increase in its volume fraction increases the initial stiffness, which is observed here. Hence, the initial slope of the response is increased. But it also increases the volume fraction of ITZ layer. Thus, the final strains are reduced. Since the ITZ is increased, the cracks will form more in this in higher volume fraction. Next parameter is considered is the strength of ITZ layer. The layers of strength decide the point of initial and final cracking. The stronger the layer, higher will be the final stress and strains for the material. This is observed in this result. It is observed that for change in ITZ strength to 0.5 megapascal, the final stresses is approximately increases to 20 to 22%. So the next variation performed by varying the aggregate diameter. Three diameters aggregate 16 mm, 24 mm, and 32 mm are utilized without changing the volume fraction of aggregate in each phase. Smaller the diameter of aggregate, higher will be the volume fraction of ITZ layer. Thus, final strains for the specimen with smaller aggregate is lower. So the next parameter considered is the
Nikhil,
ITZ.
would it be possible for you to wrap up in another couple of minutes?
Yes, sir. Yes, sir. The next is the conclusion. The next parameter is the ITZ thickness. The literature suggests that ITZ thickness as 0.01 mm to 0.02 mm, which is the progressive change occurring in the layer. Thus, the ITZ thickness is varied in this range. The result shows a higher final strains for a smaller thickness, as the failure is delayed in this case. Thus, it poses high ductility for the higher thickness. So to conclude the paper, the model satisfactorily represent the mechanical behavior of concrete at all load step. Valuable insight is also observed for macro properties, and significant effect of different parameters are successfully understood. Moreover, research leads us to closer to the performance-based engineering, which helps us to fulfill the uncertain future human and nature demands, along with the economic consideration. That's all my references, and thank you.
Thank you, Nikhil, for a nice presentation. The floor is open for any questions now. Anyone has any questions? Nikhil, can I ask a question while I wait for someone else to ask a question? If you go to one of your first slides where you had this diagram of a volume, yeah, 8, yes. So is it, are you making the assumption here that the aggregate is a sphere?
Yes, I wish to present this. It's a limitation of this. I removed a slide with the limitation that I have utilized only the aggregate as a spherical.
No, my question is that how important is this assumption, or how restrictive is this assumption? For example, if I now consider the aggregate not as a perfect sphere but as an ellipsoid, for example.
Yes, sir.
Okay, so how much would your analysis change, or would it become more difficult or too intractable? Do you think it is possible to extend whatever you have done for somehow an ellipsoid for aggregate? Because if you can do that, then you can slowly make it more generalized for any form of aggregate.
Yes, sir. So to answer this, the first work is done on the spherical aggregate. I'm still working on the making it as a general. So what I have understood a term of a sphericity, which can be utilized to make it as general means to introduce a term as a introduce a term of a sphericity, which captures the volume of one area, so that it can be included in the equations, and general aggregate this model can also be utilized.
Okay, thank you. Any other questions from the audience? Okay, if not, thank you very much, Nikhil, for a nice presentation.
Thank you, sir.
We'll move on to the next presentation. That is paper number A56, vibration analysis of thin plates with uncertain structural parameters, MV Ramarao and Andrew Ponik. Is someone available for the paper A56? Okay, it doesn't seem like the authors are available. So we will move on to the next paper, A55. That is reliability assessment of laminated composite plates under impulsive loads. Authors are Saurav Chandra et al. Yes, Saurav.
Yes. I think I'm audible.
You're audible. We can see you. You just have to share your screen. Yeah, we can see your screen. Now you can just make it full. You can go to slide view.
Yep.
Slideshow, yeah.
So it is you can see it, and also the movement, right?
Yeah, yes,
okay.
Yes.
Thank you, Professor Gupta. And thank to the conference committee for allowing me to present my work. So my talk today on actually the reliability assessment of laminated composite plate under impulsive loading. So in the present scenario, this is a very important work to assess the reliability of a composite plate under random blast loading. So my talk is basically the 4 aspects, that is motivation, methodology, and the results, and with the conclusion. So firstly, if we come to the composite plate, these are very much used nowadays in aerospace engineering, automobile, and civil engineering structure, and they are subjected to the various kind of loading. That is the static loading, sometime in mechanical loading like impact, periodic loading, some natural hazards like earthquake, landslide, and climatic load, and also it is subjected to some extreme event like fire, blast, etc. And the failure of the composite is needed to be analyzed to analyze the composite and assess the safety of the structure. So there is a several way, that is we can assess the first ply failure, or we can go for the progressive failure, that is we have to evaluate the ultimate failure load of that particular lamina in that way. So these are the procedure we have used for failure analysis. And moreover, in the real world scenario, the various parameters are not very deterministic, they're uncertain, like dimension, material properties, and the loading, these all are uncertain. So considering this fact, when we go for the assess the failure of a particular plate, so we have used the maximum strain criteria, maximum stress criteria, or SIU or Psi-Hill criteria. And when we have considered the uncertainty in the parameter like stiffness, resistance, and loads, and we will get the uncertain response. And from this particular response, we can calculate the probability of the failure and the PDF of that particular responses. And so for uncertainty analysis, we have some uncertainty framework, like we can use the Monte Carlo simulation, which is very time consuming but provide very accurate results. Or you can use some meta model like generalized polynomial chaos or KL expansion, like that. That is based on what the uncertainty we are considering. So considering this fact, our this work is basically wanted to assess the safety of a composite structure based on the extreme event like blast. So if we go, it is good to know the past work some. So there is some studies available, obviously, with the failure of the laminated composite plate and sail due to the static loading. Also, there is a few studies available for failure of a laminated composite plate due to the time varying load, impact load, etc. And also there is some studies available for the composite plate or sandwich plate due to the dynamic response. But all these studies are basically the deterministic study. And when we come to the uncertainty, consider the uncertainty, so we can use the Monte Carlo simulation, generalized polynomial chaos expansion, etc. And there is some studies for the composite plate, use uncertainty analysis of the composite plate using stochastic finite element model or Monte Carlo simulation. And there is also some studies available for reliability analysis using the meta model or the Monte Carlo simulation, but most of the studies are concentrated on the static load. So in that scenario, our aim is to study the reliability analysis of the composite plate under the blast loading. So this is basically the three aspects of this presentation: study the failure of the composite plate under blast load, and next we will study the reliability of the composite plate under blast load, which with a random parameters, and study the applicability of the GPC expansion as a meta model to evaluate the reliability. I'll quickly go to the methodology. So we will use the first order shear deformation theory for finite element modeling of the composite plates. So this is the dynamic equation of the undamped vibration of a composite plates. So M and K are the global stiffness and mass matrix, and P is the dynamic load vectors. And for failure assessment, we'll determine the laminar stress strain at each Gauss point. Actually 2x2 x 2 Gauss point are used here, and from that we can evaluate the laminar stress in the principal direction of the lamina. And we wanted to use the Sioux failure criteria and Tsai-Hill failure criteria for this study. And we wanted to use the fast ply failure to assess the failure of that composite plate. So basically we determine the failure index using these two failure criterion at each Gauss point and at each lamina. So we'll determine the overall maximum failure index of the composite plate, which we'll consider as a failure index of that plate. And we'll assess when we go for the time domain analysis. So we'll assess the Fi plate in the whole time domain. So when the Fi of the whole plate is greater than 1, we'll assume that plate is failed, and this is we'll do at each time step. For blast loading, we'll use the modified Friedler equation, which will consider the atmospheric pressure. These are the parameter basically, that P pause is basically the peak over pressure values, and the duration of the peak shock, that is T pause. This is the positive part, and this is the negative part of the response. And R is basically the radial distance between the center of explosion. This is basically the center of the explosion, and this is basically the composite plate. This distance is called the R, and weight of the explosion is W, and scale distance is Z. So in later on, we'll consider this R and W as a parameter to evaluate the failure of a composites. So in the reliability of the composite plate, we will have considered the blast load, the two parameters of a blast load as uncertain, that is R and W. We'll assume that basically composite plates are basically in factory made and have good good quality control. And so if we compare with the loading and the structure, so loading parameters are most uncertain than the parameters of a structure. So we'll consider only these two parameters as uncertain. And this is the probability of failure criteria. And then from that, we can calculate the reliability. So firstly, we'll show the Monte Carlo simulation. So we have to consider a large number of simulation, which is basically the N. For this study, we have considered the 6,000 sample, and the samples for which it is failed, that is the this value, that is Fi plate is greater than 1 is counted, and so that we can calculate the probability of failure of the plate. And similarly, we wanted to use the GPC expansion. This is the truncated GPC expansion. For the displacement, basically we'll express the displacement as a uncertain response, and from that we determine the stress and corresponding principal stress and check the failure criteria. This A alpha is basically the unknown time dependent parameter, and this is the multivariate orthonormal polynomial. So we will use some regression at each time step and calculate the time dependent unknown coefficient, and we can evaluate the D, that is the response. So in the same way, we'll determine the number of failure count using the Monte Carlo simulation. So this is and then we can calculate the probability of failure, and thus the reliability of the plate. So we'll come to some results. So in the results, so we'll show that basically we'll calculate firstly we'll calculate the deterministic failure load of the composite plate, and also then we'll come to the probability of failure while considering the two parameters as uncertain. So we'll consider the plate, which is size of 400 by 400 by 10 millimeter, and with the simply supported condition. And finite element modeling, we have used the 6 by 6 mesh size, and that is our results. That is, we'll consider the symmetric cross ply laminate and symmetric angle ply laminate, and using the psi-U and psi-Hill criteria. So just for example, I will show that how we will calculate at each time state we have calculated the failure criteria, and here the first fly failure is happen in where the maximum displacement, probably that is the maximum displacement is happening. So this is the time dependent response of the symmetric cross ply laminate using the psi-U criteria. So if we go to the results part in that table, so it is observed that we will consider here the R as a constant, that is the radial distance between the blast and the plate as a constant, and we wanted to identify the WF, that is the explosive weight at failure. So that is actually our failure parameter. So this is, if we see that basically cross ply laminate using the both failure criteria is giving the higher load, whereas the angle ply laminate is giving the lesser load. So basically this can be stated that for the cross ply laminate we are getting the higher load because the load distribution is along the X and Y direction, and in the fibers are for the cross ply laminated oriented in the X and Y direction. So in that cases there is actually along this direction the fibers are oriented. So failure along this direction is not happening for the symmetric cross ply laminate, whereas for the angle ply laminate failure is basically in the transverse direction. So that is why the symmetric cross ply laminate is giving the higher load carrying capacity. But when we see that, compare these two failure criteria, basically SIUP criteria used for the symmetric cross-ply laminate actually giving the higher load. That is, we are assuming that this is due to the consideration of the linear stress term in the SIUP criteria. Actually, in the SIUP criteria, there is a linear stress term are coming. So if we go back to the formulation part, just here, actually this stress term are coming for the SIUP criteria. So that is why the symmetric cross-ply laminate are showing the higher load. And come to the reliability analysis. For the reliability analysis, actually we consider the W and R as the random parameters, and they are actually the normally distributed. So while calculating,
can you please try to wrap up in another 2 minutes? Okay.
I'm just coming to an end. So W mean we have calculated, which is basically the 75% of the failure index we have calculated, and corresponding W is considered as the W mean, and 20% of the standard deviation, and that's 20% of the W mean. And this is the reliability. So we have calculated using the Monte Carlo simulation and the third order GPC expansion. And if we see the results, the both, that is Monte Carlo simulation and the GPC expansion, both are giving the very comparable results. However, angle ply laminate showing the higher reliability than the symmetric cross ply laminate, because actually it is assuming that because this cross ply laminated have the very low failure, that is low explosive weight, explosive weight at failure. So that is why these are giving the high reliability. This angle ply laminate are giving the high reliability. So I will come to the closer. So we have actually discussed the methodology here. So we use the finite element formulation and the fast fly failure and load for composite plates to analyze the blast failure parameters and also conduct the reliability assessment. So here we have found some salient conclusion that symmetric cross ply laminate offer better blast resistant. However, symmetric angle ply laminate exhibit high reliability, whereas the GPC expansion method we have used here have a good comparable result when we will compare with the Monte Carlo simulation. So this can be used, the GPC expansion can also be used for this analysis, while we will consider the R and W as a random parameters. So thank you.
Okay, very interesting presentation, sort of.
Thank you.
Okay, the floor is open for questions now. Anyone? While we wait for people for some questions to come, can I ask something, Saurabh?
Yes, sir.
You are essentially doing a transient dynamic analysis here. Is it correct?
Yes, true.
So I didn't quite get what are you doing there? I mean, are you developing a finite element model and then doing analysis, or I didn't quite get that part. Could you please just elaborate on
that? Yes, actually, I have. Actually, I have developed the finite element model. Actually, generally, what we will do for the static analysis, we have the only one displacement. So then we go for the failure analysis. But here, actually, for the transient analysis, we will do the failure, check the failure of that composite. That is, we will apply this failure criteria at each time.
Okay, understood. The other question that I had was that is there any reason why you did not consider random field models? Because random variable models is basically you are assuming that the correlation length scales are much greater than the spatial dimension of your structure. Okay, that's when you typically consider random variable models. And when you are dealing with large, you are considering only a 6x6 plate. But when you are considering very large structures like an aircraft or a fuselage of an aircraft, or even the wind turbine wings and so on, I mean, there the length scales are very large. So would it does it not mean that you should consider random field models rather than random variable models?
Yes, that is very important. I also thought like that. So we can use the KL expansion incorporated with the GPC. So that is also for the just we have initiated that study. So I just started with that with only the random variable. So we can also extend it with the random field model. So there is a lot of uncertainty in the fiber orientation and all that. So we can consider this also.
That anyway, right now you have not considered any uncertainties in your material properties. You have considered only uncertainties in your loadings.
Yeah, only because we just wanted to check with the only the blast, because our assumption is basically that it is the composite plates are manufactured in the control condition. So in a like a very sometime in the civil engineering structure that comparable to the blast loading, the uncertainty of the load is higher than the material property. So that is why I only consider randomness in the loading, not in the material properties.
Right.
But we can also include that.
Yeah. Thanks, Saurav. Is there any other questions? If not, thank you very much once again, Saurav.
Thank you.
And we move on to the last presentation, A14. This is experimental investigations on creep of concrete, statistical analysis of creep strain scatter by GS Vijay Bhaskara.
Am I audible, sir?
Yes, you are audible. Yeah.
Sharing my screen.
Yeah, we can see your slide number 22.
Oh, hello.
Hello. Yeah.
Good evening, one and all. My topic, I myself Vijay Bhaskara from CSIR SCRC, and co-authors are Dr. K. Balaji Rao and Dr. M. B. Anu. My topic is on creep of concrete. Here, what we try to understand the mechanisms of concrete, creep mechanisms of concrete, how it creep strains evolve with the time, and using the retardation spectra concept and some statistical analysis for how at different time scales how this creep strains manifest. Motivation of this is recently accurate prediction of time dependent deflections are at a design stage itself is very important for considering serviceability of structures. But if you see the existing bridges, a lot of old bridges are, excessive deflections are being observed, and none of the models are able to, none of the codes are able to predict the excessive deflections in precious concrete bridges. And we can see recently, many bridges have been, a lot of excessive deflections have been observed, which shows that there is a need to predict a more rational creep prediction model. So time-dependent deflections are mainly affected by time-dependent properties of concrete, such as compressive strength development with time, modulus of elasticity with time, and creep and shrinkage. In this topic, we will be concentrating today on creep and shrinkage. So creep is the time-dependent increase in strain in hardened concrete under sustained load, which can be classified into basic creep and drying creep. Basic creep is nothing but when there is no moisture movement between specimen and atmosphere, we call it as basic creep. And drying creep is additional creep due to allowing moisture movement from specimen to the environment. These are the factors affecting creep. Mostly it is the mixed composition such as fly ash, water content, those things. And then with environmental factors such as relative humidity and temperature, and low applied stress level, and at what age, the strength at the time of loading, these are the important factors. Like these are the basic terminology. Like how we get here is like in the experiment, we have to test under both the loaded specimen and load-free specimen in both sealed condition and unsealed condition, so that we can get all four components of that is autogenous shrinkage, total shrinkage, and basic creep and drying creep. This is the basic terminology. And here the compliance is nothing but like load induced strain per unit stress, and the creep strain is nothing but after deducting like elastic strain and shrinkage strain. Specifically is nothing but that creep strain per unit stress. These are some of the popular research groups working in the creep of concrete. And if you see the existing prediction models, like most of the models are parameters of those models. I mean, all models are developed for OPC concrete, and all these models parameters have been estimated using the database available at the international, like which has been collected by Northwestern University by Bajan. But this accuracy of these models are based on the experimental data, what is in the database. But in the database, we can see that lot of inconsistency in testing and reporting, and most of the data is 96% of data is short-term data, and only like 2 data sets is more than 12 years, and most of the data is less than 6 years. So hence, what we in SCRC concrete creep testing laboratory has been established, and we have by considering the data, by after analyzing the database, we observed some of the observations, like many inconsistencies, and also some of the recommendations we have taken, and we have planned these experiments. Mainly to understand how the creep strain evolves at different time scales, and how and also the creep mechanism. So here we are the experiments are being conducted. Now we have about 5 years of data is being presented here, and it is the experiments are still being continued. Grade of concrete which we use is M40 concrete, and for to get the basic creep and autogenous shrinkage, that sealing material, that self-adhesive aluminum foil tape we have used for sealing, and embedded type vibrating wave strain gauge has been used. That is mainly because in from database we observed most of the data they are measuring using surface strains using that friction based, which is not reliable. So embedded type vibrating wave strain gauge we have used. These are the characterization of materials which we have used. So this shows that this figure shows that the strain development in individual specimens. Here we have about that is for each different set three specimens we had tested, that is under loaded condition, load-free condition, and also sealed condition and unsealed condition, so that we can get the all component of creep and shrinkage. So here we shows we have about 4 years of data, and for OPC concrete, F30 concrete, F40 concrete we have tested. So if you see the data, how important, for example, if you consider IS 456, which gives only like if we load at the 28 days, creep coefficient is only 1.6. Here it is like 1.6. From this data itself, we can show now our data itself shows like in 4 years it is about 3.1. So how much like we are under predicting using this, and it is actually creep is it is a time function, but in IS 456 we have only 1.6, and it is drastically, and also from literature we can note that creep will be about 3 to 4 times of elastic strain, but what we are considering in codes is just 1.6. That may be the reason. So in case of precious concrete bridges, more creep happening, so more street when precious loss, as the length of beam is shortening, that precious loss will be there, so that which leads the deflections. Once it is deflected, I mean cracks will appear. Obviously it will expose to the chloride environment, and spalling will occur. These are the typical scenario in many of national highway bridges. even in IS 1343 code, latest, which has been the FIB code model, form of the FIB code model has been adopted. That model also has been like under predicting the creep strain, which can able to capture only that basic creep part only, not the total creep part. Which shows the importance of like developing the model. And also for Indian conditions, there is not much like long-term creep testing data, experimental data is not available. So that this data will be useful for developing models. And if you see the average strains in like sealed, unsealed conditions, these are the things. And creep rate has been calculated using ASTM C512 code. And if you see the creep rate here, that since like here initially it was increased, then it is started reducing due to since at later ages basic creep rate creep rate in basic creep response is higher. Initially in like due to drying, creep rate in total specimens is higher. Here we can note that from literature only decrease in creep rate is observed. That initial part in first 2-3 minutes, that increase in creep rate is not observed. That is because the initial reading after loading has been recorded after several minutes and hours, based on the type of the machine. Like if it is a spring type machine, for loading they are taking more time, and after 2 hours, like after 3 hours only, they are taking the reading. By that time, lot of creep would have happened. But here we have some sophisticated machines we have used, and using this high speed data acquisition, we could able to capture this increase in creep rate also. So when we compare with that, for example, for right now for fly ash concrete, we have only one model, that is B4 model. When we compare with the B4 model, only for basic, it is able to predict for basic creep of the OPC concrete, but for the fly ash concrete, it is over predicting, like B4 model in both the F30 as well as F40 concrete. Mainly due to that model parameters, what we that B4 model is, that is the only model available. That is also has been, that parameters has been estimated using limited test data. That is, if you see more than 30% of fly ash, only 4 concrete mixes, and a total of only 23 concrete mixes, and more the concrete having more than 30% have only 4 concrete mixes, which shows the importance of this data. It will be, which will so it shows which will, this data will be very useful. And here, so here main aim is that the scatter will be from creep scatter will be very high, and if it the influence of humidity, RH, and other mixed component has been extensively studied. So here what we are considering, only we are interested in understanding the creep mechanism. That is everything, all the factors we kept same, and from the creep mechanism, how the dispersion, how it is varying with the time, we want to see. So in the same loading machine, we have loaded 4 specimens, and in same conditions all the specimens have been tested. What we did is, from measured strains, we have taken out the shrinkage strains and elastic strains, and based on the slope of the average creep strains and keeping the sample size same, the creeps curves are divided into 26 segments, and at each point of time that mean strains are deducted, so that to get the creep strain deviations, and histograms of the squares of this the creep strain deviation are plotted for each segment. This is the mean value, how it is for each segment. But if you see the deviations, like initially it was during unimodal, then it was like bimodal, then it was coming like 3 modes are coming in picture. Like if you see same thing here, like creep strain scatter alone instead of scatter. Initially it was unimodal, then bimodal, then trimodal at a different time scales. This may be due to, when we compare with the before model, that is like we have different components of creep, that is like aging and non-aging viscoelastic, and flow creep, and the drying component of the creep. So you see, during time of at the time of unimodal period, that contribution from viscoelastic is coming more. So that's why we call it, it is showing maybe for unimodal. Then from after 1 day, that drying, the contribution from drying is started picking up. So it may be showing that bimodal. Then at the later ages, all three mechanisms are in place. So so we can see the trimodal. So to understand better these mechanisms, what is at how this creep strains, why it is happening at different time scales, what we do, we have used the retardation spectra concept. So here, this spectra will be very useful. What we are getting from experiment is macroscopic deformations, but using this spectra, we can understand what's happening at the microscopic level. As Costa established, told that DRS can be used to identify number of mechanisms that might possibly govern the creep of concrete and also the time range of the influence. So if you see here, that is nothing but it is a Kelvin chain, and initially the attached with the elastic spring for capturing elastic strain. See, these are the number of Kelvin units, Kelvin chain, and this is the creep compliance function. This is the creep compliance function. Discrete retardation spectra is nothing but that it is the plot between compliance and retardation. But here it is main important thing here is from the literature, from each test we have limited test data points. Like they have about only 6 points or 10 points like that. From each data point, from each test they have less number of data points. So that they could not able to, from literature data, we cannot obtain all the peaks which are at place. So only one peak or two peaks we can get. So far models have been, till now has been developed by considering only one peak, and after that Bajant has been identified one short-term peak and one long-term peak, and only two peak has been developed. That is the latest model, that is B4 model, B3 and B4 model. Bajant has developed by considering two peaks. That is mainly due to the number of points from each test was very less. But in our the experiment, we have planned such a way that we measure at the center of the cylinder and also at the closer interval of time, and initial reading also from instant of loading we are taking. So this.
Can you please try to wrap up in 1 more minute, because we are already 4 more.
Yeah, sure, sir. This is the procedure for obtaining the discrete retardation spectrum. Main idea here is what is it? To get to choose the retardation time at the logarithmically equidistant spacing. This is the retardation spectra. Here we are observing for total creep, there is 3 short-term peaks and 2 long-term peaks. There are about 5 peaks are coming. And here it is about for the basic creep, it is 2 peaks and 2 short-term peaks and 2 long-term peaks. This is for the basic creep. And here again we carried out the statistic analysis for each peak, that is valley to valley for each peak. The time corresponding to valley we have taken, that creep strain deviation has been plotted. And here it shows for initially that for the histogram plot corresponding to first peak is shows unimodal, then bimodal, then it starts dispersing. So this may be due to as micropressure solidification theory by Bajant says, it is that creep is due to viscous shear slip, that is due to change in the micropressures that cross across micropores of the concrete. That change in micropressures is happening due to moisture movement at a different size of the pores. If you see the concrete, there is capillary pores, gel pores, as well as interlayer pores and other features. See, if in case of capillary pores, the moisture movement is relatively faster and reversible. In case of gel pores, it is slow and only it can be recoverable only to some certain extent. And in case of interlayer, this one, it is happening under severe driving. It is almost irrecoverable. That is contributing to flow creep. So this is the reason. Moisture movement at different pore sizes is the reason for change in micropressures. That's what we got from discrete retardation. To conclude, that the experimental data, what we have about 7 right now presented for 4 years, but we have about 7 years and it will be still continuing. And using reliable concrete creep testing data, and we have obtained the discrete retardation spectra, which shows for the first time, it shows that 3 short-term peaks and 2 long-term peaks. This is very crucial for developing a rational creep prediction model. And the statistical analysis of creep test data shows it is a non-stationary process, and that the evolution strains in individual specimen is sensitive to differences in moisture content field due to heterogeneity structure of the concrete, heterogeneity of microstructure in the concrete. Then due to high-speed data acquisition, for first time we have noted that the increase in the creep rate in the first few minutes, that is due to micro cracking and thereby progressive. Then these peaks, what we observed in DRS is is due to change in the microprecious caused by the movement due to hydration and drying process at different pores of different sizes in the pore system of the concrete. Thank you. Thank you.
Thank you, Dr. Vijay Bhaskar. It was a very interesting presentation. So the floor is open for questions. Any questions? I am not really in this area, so I didn't quite follow. But if you can, you please go back to your slide number 25.
Yes, sir. Yes, sir. Yes.
No, not 20, 25. Yeah, this one. So this is from the same number of samples, right? All these histograms, or it's different? Because in the histograms that we see that I don't think the number of samples for the different points that we have are the same.
So what we have taken in this point here is like from valley to valley, time corresponding to each week. That data points we have taken.
No, what my question
is sample size is differing, sir. Yeah,
different. Okay.
But
it's not that you are taking one sample and then you are for a long time you are doing this test. It's not that.
Yes, sir. Yes, sir. But here in the first time what you have shown earlier in slide number 19, here sample size is same. Based on the slope of the creep rate, we have divided into different time segments, and then here we kept the sample size as same. But here also we are seeing initially unimodal, bimodal, and tripodal.
Okay.
Thank you, sir.
Yeah. Any more questions? Okay. If not, thank you, Dr. Vijay Bhaskar, for a nice presentation and an interesting topic. So I think with this, we come to the close of this session, right? We don't have speaker A56 is not yet available. So I think with this, I think we had an interesting session. We had 4 papers. The first paper talked about probabilistic model reduction in the analysis of randomly parametered building frames subjected to sudden loss of columns. Then we had a presentation by Nikhil where he the role of interfacial transition zone on the response of concrete under tension using a micromechanical approach. Then Saurav presented a paper on the composite plates under impulsive blast loadings. And finally, the last paper was on statistical analysis of creep strain scatter. So it was a quite a broad range of topics that we have discussed in this course. In this session. Yeah. So I think with that we come to the end of this session, and it's also the end of the day, right? Yeah. So is there anything that we would like to discuss?
No, sir. On behalf of the organizing committee, we thank Professor Sayan Gupta for conducting this session, which was lively and very much interactive.
Okay.
Yeah, we thank you, sir.
I think
with this, we come to the end of day 2 session here. And as usual, tomorrow with the same link, we'll start the keynotes talk and followed by the technical sessions in the same link at 3 o'clock. Thank you all.
Thank you, sir.
Thank you. Thank you.
Thank you. Bye. Bye-bye.
I'm stopping the recording and ending the meeting as well.
Yeah, thank you.